A spacecraft sits in low Earth orbit, refueled and ready to begin its trip to Mars. On the navigation display, the route appears as a long curve with an estimated travel time of 7 months one way. The crew is sealed inside a metal tube and will be moving through radiation month after month, with only a thin layer of water inside the walls protecting their bodies from radiation. Every system on the ship exists to keep them alive on the way there and back. Now imagine you could swap out the fuel for the most energy-dense fuel known in physics. A tiny mass of it carries more energy than tons of anything we currently burn. The spacecraft would not need to drag so much of its own fuel across space. More of the mission could be spent moving, and less of it spent enduring the slow cost of getting there. The trip should shorten significantly. The crew should step onto Mars stronger, healthier, and less exposed to everything deep space does to the body. That is the promise of antimatter propulsion. It is why engineers keep returning to it, decade after decade. But the closer we look at it, the more complicated it becomes. Antimatter is not fuel in the ordinary sense. You cannot just store it, open a valve, and send the exhaust out the back. The same reaction that makes it so tempting also makes the spacecraft harder to build, harder to shield, and harder to keep people safe inside. So the question for tonight is simple. Could antimatter propulsion really take us to deep space? If you enjoy exploring questions like this with me, subscribing to the channel helps others find them too. Liking and sharing the video helps even more. Let's begin. Hold that ship in your mind. A standard chemical or low-thrust ship leaving Earth for Mars has to coast through most of its trip. The trajectory engineers draw is a Hohmann transfer, an unhurried arc that takes around 6 to 9 months out, and roughly the same to come home. In between those two arcs, the crew waits on the surface for the orbits to line up again. The whole round trip can run 2.5 years. The fuel for that mission is mostly spent at 2 short burns near the start and end of each leg. Almost everything else is patience. The vehicle's mass, its food, its water, its shielding, its spare parts, its psychology, all have to survive the months in between. The reason is simple. A faster trip helps the crew and helps the ship. Cosmic radiation accumulates with time. Bone density falls with time. Equipment fails with time. The galactic radiation a crew picks up across a Mars trip is one of the harder problems in human spaceflight, and the dose climbs the longer the ship is on the way. Studies of long-duration cruise on the International Space Station already show changes in eyesight, balance and white blood cell counts after 6 months in a much friendlier environment than open interplanetary space. Mars, on a Hauptmann arc, demands twice that exposure outbound, then a long surface stay, then twice again inbound. Any fuel that could cut transit by a large factor would shorten the dose, shrink the food and water mass, lower the failure mode count, and turn Mars from a frontier expedition into something closer to a long deployment. That is why antimatter keeps coming up in mission studies. The energy locked in a small amount of it is, on paper, a real answer to a real problem. There is also a psychological piece that does not show up in the rocket equation but shapes every program. Inside a small habitat that smells, by month 6, of recycled air, sweat and stale food, the crew has to wake up, eat, exercise, do science, sleep and not break each other. NASA flight medicine has been studying this since the early days of long-duration spaceflight, and the picture from the ISS, from Mir, and from Skylab is that humans survive long missions, but they are not the same humans at the end. Hand strength falls, bone density falls, eye pressure changes, mood drifts, even with the best onboard exercise. The body does what the body does in the absence of gravity, and time is the slowly turning crank that drives most of it. A fuel that could turn 9 months into something close to 1 would not only spare the crew radiation, it would let them stop becoming a different version of themselves on the way to work. The math is the kind that gets bookmarked in propulsion classes. 1 kilogram of antimatter combined with 1 kilogram of normal matter, fully annihilated, releases on the order of 9 times 10 to the 16th joules. That is more than 1,000 times what a kilogram of fissile uranium, 235, gives up in fission, and over 10 billion times what a kilogram of the best chemical rocket fuel releases on burning. If even a small slice of that number ended up in directed exhaust, A Mars ship would not need a propellant tank larger than the rest of the spacecraft. The dry mass would dominate. The trip time arithmetic would bend. NASA Marshall Space Flight Center's Antimatter Propulsion overview puts those specific energy comparisons side by side, not as marketing material, but because the comparison is the part of the story that earns the rest of the conversation. That energy density is why engineers keep checking the concept instead of discarding it outright. But move the camera close to the tanks of an antimatter ship for the first time, and the obvious picture breaks. Ordinary rocket fuel sits in pressure vessels that look like grain silos with valves. Antimatter cannot live in a vessel like that. The moment it touches the wall of an ordinary tank, it annihilates with whatever it touched, and the wall and a sliver of the surroundings. So the fuel bay is not a container, it is a trap. CERN has used Penning-style traps to hold small numbers of antiprotons for hours and antihydrogen atoms for minutes, by suspending them in vacuum inside crossed electric and magnetic fields. Those traps are kept under hard vacuum, cooled to near absolute zero, and built around superconducting magnets that themselves need power and cryogenic plumbing to stay alive. Translate that to a spacecraft, and the fuel storage system is suddenly a machine that must run every second of the mission, with no off switch. That is the first crack in the easy version of the story. Step further into the design, and the consequence reaches the people. Antimatter does not annihilate quietly. A proton meeting an antiproton turns most of its mass into a burst of energetic particles, and a large share of those products are gamma rays and neutrinos that do not care about magnetic nozzles or shield doors. They travel in straight lines through walls, through people, through electronics. The ship cannot simply tuck the engine into an aft compartment and hope. Standoff distance becomes a structural requirement. The crew compartment, the avionics, the fragile science instruments, all have to move away from the engine along a longer truss, behind heavier shadow shields, with the engine essentially aimed at a small slice of empty sky. The crew capsule, the radiators that bleed away absorbed heat, and the science package all migrate forward of the shadow shield, and the structure between them and the engine becomes part of the propulsion system in everything but name. There is one more thing to notice while the ship still looks normal. The propulsion engineer who first sketched an antimatter rocket on a notepad did not have to invent the physics. The annihilation reaction has been studied at CERN for decades. The Penning trap was developed for precision measurements in atomic physics and won a Nobel Prize for that work in 1989. The magnetic nozzle concept borrows from plasma propulsion research that already exists for other thrusters. None of the pieces are speculation. They are the products of established science programs, used here in a new combination. That is part of why the concept has the staying power it does. It is not built on something that has yet to be discovered. It is built on real laboratory facts, asked to do a job they have never been asked to do at the scale a real rocket would need. So you can see why the idea is attractive in its own narrow way. A few grams of antimatter really does carry the energy of a city, but the vehicle that has to feed on those grams, hold them, fire them, and survive what comes out the other side, is already shifting under the weight of its own engine before the launch pad even appears. If antimatter is the obvious answer, why does the ship still look fragile? That is what the rest of tonight's argument is about. Set the storage problem and the radiation problem aside for a minute, and stand inside the part of the story that pulls people in. The reason serious researchers keep writing papers on antimatter propulsion is not science fiction. It is a sober energy comparison, the kind you can do on a napkin and then defend to a referee. When matter meets antimatter, essentially all of the rest mass on both sides turns into energy according to Einstein's mass-energy relation. The specific energy of equal parts matter and antimatter is around 9 times 10 to the 16th joules per kilogram of the combined mass. In NASA Marshall's antimatter propulsion deck, the same number is set beside chemical fuels, fission and fusion. Chemical reactions release a few tens of millions of joules per kilogram. Pure fission of uranium, 235, releases about 80 trillion joules per kilogram. Deuterium-tritium fusion releases roughly 340 trillion. Annihilation is more than 300 times denser than fusion and roughly 10 billion times denser than the best chemical fuel. Translate that into the language of mission planners. A Mars-class spacecraft using chemical rockets typically carries a propellant mass that dwarfs everything else on board. The vehicle that lifts off looks like a fuel tank with a small crew can on top. Even for nuclear thermal propulsion, where each kilogram of propellant carries more energy out of the engine, the propellant tanks remain large compared with the rest of the ship. Now imagine a propellant whose energy content per kilogram is, on the page, hundreds of millions of times higher than chemical fuel. The propellant mass collapses. The dry mass of the ship suddenly looks dominant. The trip time math, which always pits how fast you can move propellant out the back against how much you have to carry, suddenly looks like it might bend in your favor. That is the seduction. Not magic, just an enormous specific energy that is real and measured, sitting in the mass energy equivalents on every textbook page. The other piece of the seduction is sheer ratio. Even fusion, which is itself a long-running ambition for propulsion, gives back less than 0.5% of its rest mass as energy. Fission gives back even less. Chemistry gives back vanishingly little. Annihilation, when it happens cleanly, hands back essentially everything. 2 kilograms in, 2 kilograms worth of energy out. There is no upper layer of physics waiting to take a bigger share. The conversion ratio is the maximum allowed by the rules of the universe. That is the part that keeps the conversation alive across propulsion conferences. You can imagine a future fission rocket. You can imagine a future fusion rocket. You can imagine future chemistry that is slightly better than today. None of those concepts, at their best, sit anywhere near where antimatter sits. It is the boundary. Everything else is somewhere below it. It also has the benefit of being clean. The fuel itself is exactly the antiparticle of one of the things the spacecraft is already made of. An antiproton plus a proton makes a small particle cascade and disappears, leaving no ash, no slag, no spent reactor core, no waste to dispose of in a vault on Earth. CERN's public material on antimatter notes the same point. This is matter in a form that simply cancels its counterpart completely, with nothing left over to bury, compared with fission, where the most pressing political problem is what to do with the long-lived isotopes after the engine has cooled. Antimatter looks like an engineer's daydream. The promise stacks up cleanly: higher energy density, no chemical waste stream, no fission products, no contamination of the spacecraft structure that lingers for years after a burn. But then the second story starts, and it starts inside the engine bell. Move closer to the moment of annihilation. A proton-antiproton encounter does not produce a single tidy puff of light pointed backwards. It produces a small cascade. On average, the reaction makes a handful of pions, about 1.5 neutral pions and about 3 charged pions, with smaller branches into kaons and other heavy quark products at higher energies. The charged pions are the part that looks like rocket exhaust. They carry electric charge, which means a magnetic field can push them around. But charged pions are also unstable. They live for about 26 nanoseconds in their own frame before decaying into muons and neutrinos. At relativistic speeds, they fly farther, but not forever. The neutral pions are worse. They live for less than 1/10 of a femtosecond and decay almost immediately into 2 gamma rays each. Those gamma rays move at the speed of light in random directions and care nothing for the engine. They cross the chamber wall before any field has time to nudge anything. There is also a temporal piece that surprises people. Because the charged pions live only tens of nanoseconds, the engine has to extract their momentum within tens of nanoseconds of their creation. That is fast by spacecraft standards. The magnetic nozzle's field has to be set up before the annihilation event. The field has to act on a particle that already exists. There is no time to switch the field on in response to anything. The nozzle, in other words, is not reactive. It is a static field shape that catches whatever passes through, and the catching has to happen quickly. That puts a hard constraint on how complicated the field can be. Designs that ask for active control of the nozzle field on nanosecond timescales are not realistic. Designs that ask for a clever fixed field shape are. So the engineer hands the engine bell a problem it was not designed for. The original picture was: ignite, point the plume backwards, ride the recoil. The real picture is: stage a cascade. sort which products are still around long enough to steer, accept that a large share of the energy was emitted as gamma rays that already left, and try to extract thrust from what is left. That is not a footnote on the energy comparison. It is the first place the comparison starts leaking. The pure annihilation number assumes you can collect every joule and aim it. The actual reaction insists on giving you a fraction at best. Even before any of the other costs are counted, the headline number that made the slogan possible is already shrinking. There is a useful number to keep in mind when reading antimatter literature. Even with an optimistic nozzle that catches a substantial slice of the charged pion energy, the maximum directed exhaust speed of an annihilation rocket comes out around 1/3 the speed of light, not the speed of light itself. That is still a number propulsion engineers would write home about. Chemical rockets get exhaust speeds around 4 km per second. Nuclear thermal rockets reach about 10 km per second. Even optimistic fusion concepts struggle to break a few percent of the speed of light. The antimatter number, around 100,000 km per second, is in a different league. But it is the league that physics actually allows, not the league the original specific energy alone implied. That fraction, before any nozzle work, before any losses to neutrinos, before any shielding, is roughly what the rocket scientist gets to play with. The remaining majority is the bill the rocket scientist has to pay. If the energy case is this strong, where does the gain start leaking away? It leaks at every step that turns physics into a working spacecraft. The simplest way to feel the second cliff is to walk into a real antimatter facility and watch what an entire year of effort actually produces. CERN's antiproton decelerator is the only place on Earth that supplies low-energy antiprotons to experiments. It takes high-energy protons from CERN's accelerator chain, slams them into a fixed target, captures the rare antiprotons that come out of those collisions, cools them, decelerates them, and feeds them to teams working on anti-hydrogen, gravity tests, and atomic physics. The whole machine is the size of a building. It is one of the most demanding pieces of equipment humans operate, and the amount of antimatter it produces is, in mission terms, almost nothing. In broad numbers reported by CERN itself, all the antimatter ever produced by the laboratory across decades of operation, if it were collected and annihilated at once, would release on the order of a few nanojoules of energy. That is not a typo. A nanojoule is a billionth of a joule. Producing the entire human stockpile of antimatter releases less energy than lifting a small fly by a centimeter. The reason is not laziness or budget. It is the production method. Bombarding a target with protons makes antiprotons as a rare side product with extremely low yield. Almost all of the input energy ends up as heat in the target, electromagnetic showers, and other particles. Only a tiny fraction is recovered into trapped antiprotons. The laboratory was built to do precision physics, not to fill propellant tanks. That is the heart of the present-day production scandal. To make antimatter, you spend an enormous amount of input energy and recover, in the form of antimatter, less than 10 to the minus 10 of what you put in. Some published estimates put the round-trip energy efficiency closer to 10 to the minus 9 when you include the cost of capturing, cooling, and trapping the antiprotons after they are made. A rocket-scale fuel economy, where you spend a power station to produce a few nanograms of fuel, is not bad in the way a normal engineering trade is bad. It is bad by 10 orders of magnitude. Any concept that relies on burning more than a small amount of antimatter has to invent a new production method first, then replace the current one. The current method is the wrong shape for the problem. There is a piece of the picture that has improved since the early days, and it is worth crediting honestly. Decades ago, the few traps that existed could hold a handful of antiprotons for seconds. Now, between the antiproton decelerator and the lower energy EL ring that feeds it into modern experiments, CERN can deliver pulses of millions of antiprotons at low enough energies to be slowed, trapped, and combined with positrons to make antihydrogen. Each step on that ladder has taken years of careful work. The fact that there are now several long-running antimatter experiments at the same facility, sharing the same beam, is genuine progress. But the ladder leads from a few particles to many particles in a trap, not from many particles to mission-relevant masses. The slope is the wrong shape for fueling rockets. Even setting efficiency aside, the raw throughput is small. CERN, on a good year, produces something on the order of 10 nanograms of antiprotons across all of its experiments. Almost all of those antiprotons are consumed in the experiments themselves, in collisions that test fundamental symmetries between matter and antimatter, in spectroscopy of antihydrogen, in measurements of gravitational acceleration on antimatter. Very few are stored for any length of time. The annual deliverable to anyone outside the experimental teams is essentially zero. You cannot buy a gram of antiprotons. You cannot rent a milligram. The supply chain does not exist because the supply does not exist. There is a useful way to picture the production gap that has nothing to do with rockets. A single nanogram of antimatter, fully annihilated with matter, releases about 1/10 of a joule of energy. Lighting a wooden match releases roughly a kilojoule, or 10,000 times more. So the entire annual antiproton output of CERN, if collected and ignited at once, would still be less energetic than striking a match. That is the production base humanity has built across decades of careful experimental physics. It is a beautiful achievement for fundamental science. It is a sobering starting point for propulsion. Bring that back to the Mars ship and the comparison gets brutal. Existing pure antimatter mission concepts in the literature, at their most modest, ask for milligrams to grams of antiprotons to do useful interplanetary work. The most ambitious ask for much more. A whole year of operating CERN's facility produces something like a few nanograms of antiprotons, and most of those are consumed in experiments, not stored. To go from a few nanograms a year to milligrams or more, present production would have to improve by something on the order of 1,000,000 to 1,000,000,000 times, and the energy cost ratio would have to improve along with the yield. That is the bill in plain numbers. Not impossible by physics, far from possible by the present industrial base. There is also a planetary perspective worth a moment. The total electrical power consumption of human civilization runs in the tens of terawatts. If a dedicated antimatter production facility ran continuously at present efficiency, it would need a substantial fraction of a country's electrical grid to produce a few grams a year, with no other use of that energy. Spending a national power supply to charge a rocket fuel tank, when the same energy could just be used to push a different rocket, is the kind of trade that has to be defended very carefully on the engineering side. The defense usually rests on the special properties of the antimatter rocket that no other engine offers. The maximum specific impulse, the smallest propellant mass for a given mission, the only known route to certain extreme delta V values. Those arguments are real. They also live a long way from the present industrial base. There is also a final thought about how the technical answer ages. The propulsion field does not stand still. New superconducting materials may make trap magnets lighter. New target geometries may improve production yield. New chemistry may make catalyzed concepts more efficient. The bounded answer about antimatter today is a snapshot of the present state of the field. In 30 years, parts of that snapshot may shift, even if the energy density and the limit case status do not. There is also a question of input form. Modern production uses high-energy proton beams hitting a fixed target. Future production schemes have been sketched in the literature. Positron production via dedicated beams, antiproton production using more efficient interaction geometries, or even speculative schemes that use astrophysical sources rather than terrestrial accelerators. None of those schemes has been demonstrated at any useful scale. The basic process by which antimatter is created on Earth has not changed much in decades, and the efficiency of that process is set by the fundamental ratio of cross-sections for the relevant reactions. Improving the production efficiency by orders of magnitude would likely require a different physics approach, not a better engineering of the same approach. Until that physics is developed, the production scale stays roughly where it is. The mission planner does not get to pretend that bill will be paid by inertia. Even if you imagine a future where dedicated antiproton factories run continuously, fed by their own power stations, every joule of energy used to make antimatter is energy that did not push a spaceship directly, so the fuel only earns its keep when the storage and use story is good enough that the indirect path is still cheaper than just using the original energy source. That is the part of the argument that has not been won. The energy efficiency of antimatter production must rise by orders of magnitude before the round-trip math turns positive on its own. Until it does, every gram of antimatter on a spacecraft is in effect a gram of prepaid grid energy converted into a particularly difficult to store form, with all the conversion losses already baked in. If making the fuel is this hard, what happens once you try to carry it anywhere? Step inside the fuel bay of the antimatter ship. The bay is a vacuum chamber. The walls are thick and shielded. In the middle is what looks at first like an empty space, suspended by magnetic and electric fields, held under continuous control. There is no liquid level. There is no drum. There is no valve to a pump. The fuel is a cloud of antiprotons or antihydrogen atoms, kept away from every wall by the only mechanism that can keep them away from every wall, which is the field itself. This is a penning trap and its descendants, scaled up from the laboratory and asked to do something they were not originally built to do. Storage is not a state here. It is a process. The trap is on, or the fuel is gone. Even on the lab bench, this is hard. To hold antiprotons, you need a deep magnetic field, an ultra-high vacuum better than 10 to the minus 12 torr, and cooling that brings the trapped particles into thermal equilibrium with their surroundings. The ALPHA experiment at CERN trapped a few hundred antihydrogen atoms for around 1,000 seconds in 2011. That was a landmark. To put a number on it, a few hundred atoms is many orders of magnitude fewer particles than even a single thread of human hair. For a mission, you would need to scale that by many orders of magnitude in trapped quantity, and stretch the holding time from minutes to the full duration of the cruise, which is months at a minimum. The trap therefore stops being a piece of equipment and becomes a whole subsystem of the spacecraft. It has its own mass, its own redundant magnets, its own cooling loop, its own vacuum pumps, its own diagnostics, its own failure tree. The reason vacuum and cold matter so much is that the antimatter cloud is in a constant negotiation with the residual matter inside the trap. A single stray atom of normal hydrogen drifting through the trap volume finds an antiproton or an antihydrogen atom and annihilates with it. Even at the spectacular vacuum levels achievable in modern laboratories, there are still some residual gas atoms inside a trap of any reasonable size, and each one represents a slow drain on the stored inventory. Lower temperatures help, because the residual gas freezes onto the walls and stops drifting through the active volume. Better vacuum helps, because there is less gas to begin with, but neither is free. Better vacuum pumps and colder cryogenic systems add hardware mass and continuous power draw to the spacecraft. The trap is also picky about what it shares space with. Stray electric and magnetic fields from other equipment can perturb the confining field, and even small perturbations can move the cloud toward the wall. So the magnet has to be magnetically shielded from the rest of the spacecraft, and the rest of the spacecraft has to be magnetically shielded from the magnet. The avionics nearby cannot use components that would saturate in a high field. The cabling nearby cannot run currents that would warp the trap's confinement. Every nearby system has to live politely with the field. In a normal spacecraft, electromagnetic compatibility is a checklist item. In an antimatter ship, it is closer to a religion. The trap cares about every loose wire, every powered fan, every small current loop. A failure of compatibility somewhere far from the engine can still reach back through the field and disturb the fuel. Then ask the simple practical question: how do you move that fuel between places? Even at research scales, moving trapped antiprotons is hard. CERN runs a project called Puma that is designed to ship antiprotons across the laboratory campus to other experiments, using a transportable penning trap on a frame that is bigger than a small car. The trap holds on the order of 1 billion antiprotons, which is many billion times less than any propulsion-relevant load. The hardware required to move that small number is dominated by superconducting magnets, vacuum systems, and shock-resistant structure. The mass of the support hardware completely overwhelms the mass of the actual fuel inside. The fuel is essentially weightless. The machine that carries it is not. There is another small lesson in Puma's existence. The fact that a project to move antimatter from one CERN beamline to another required dedicated funding, dedicated engineering, dedicated hardware, and several years of work tells you something about the scale at which antimatter transport currently lives. The distances involved at CERN are walking distances. The quantities involved are millions of antiprotons. The mission distances for spaceflight are millions of times farther. The quantities involved would be many times larger. The hardware that delivered Puma is impressive engineering for its purpose. It is a long way from a hardware base that could refuel an interplanetary spacecraft on schedule. Take that picture out to a spacecraft. You do not move the fuel from a depot to the engine. You hold the fuel inside an active trap that hangs off the structure of the ship, draws power continuously, and cannot be allowed to fail. Lose the magnetic field for a few seconds and you lose the fuel. Lose enough of it at once and you lose the ship. The propellant has gone from being a passive cargo to being a continuously babysat machine, so the fuel system, instead of shrinking the spacecraft, starts to colonize it. A propellant whose energy density is enormous on paper still ends up dragging a much larger system's mass behind it. The Mars ship that began the trip as a clean line on a view graph picks up trap coils, magnets, cooling pipes, support trusses, and redundant control electronics. Energy density does shrink the propellant mass. It does not automatically shrink the propulsion mass. There is also a less obvious cost in failure modes. A trap is a continuously running control loop. The magnetic field has to be held to high precision. The electric field has to be held to high precision. The vacuum has to be maintained against outgassing from the trap walls. The cryogenic system has to keep the magnets superconducting. Any one of those subsystems fails, and the trap is no longer a trap. A trap that fails for a few seconds may lose a small fraction of its inventory to wall annihilation. A trap that fails for longer may lose the entire stored inventory in a single burst. The energy of that burst, for a mission-scale load, is large enough to destroy the spacecraft. Reliability is therefore not the kind of statistical thing that ordinary mechanical systems care about. It is closer to the kind of reliability that human-rated launch vehicles ask of their flight computers, multiplied across many subsystems and applied to a machine that has to run for months without rest. There is also a less obvious cost. Every kilogram of trap hardware you carry is mass that has to be accelerated and eventually decelerated by the same engine the fuel is feeding. So the trap is in competition with itself. Larger fuel inventories let you go faster, but they require larger traps with more confinement hardware, and that confinement hardware eats into the performance the larger fuel inventory was supposed to deliver. There is an optimum somewhere, and the optimum is much smaller than the headline energy density suggests. Once you build a trap big enough to hold mission-scale antimatter, the trap and the fuel together can easily outmass the rest of the ship. If the tank is already a machine, what kind of engine does the machine actually feed? Go forward in the ship now to the engine itself. In the Daydream version, an antimatter rocket has a chamber where matter meets antimatter, an annihilation event, and a clean jet of light or particles coming out of a nozzle. In the actual physics, the chamber is more like a particle accelerator's interaction region than a combustion chamber. When a proton meets an antiproton in a controlled annihilation, the most common outcome is the production of a small group of pions. About 1.5 are neutral on average, about 3 are charged. Above a certain energy, kaons and other strange quark products contribute small fractions, and the products themselves quickly decay into lighter particles. There is no central jet that emerges intact from a single event. There is a small spray, distributed in all directions in the rest frame of the colliding pair. That cascade is what the engine has to handle, and the cascade does not arrive as a single coherent stream. The charged pions emerge in many directions inside the annihilation volume, each one moving at a significant fraction of the speed of light, each one carrying electric charge and therefore steerable in principle by magnetic fields. The neutral pions also emerge in many directions, but they decay almost immediately into 2 gamma rays each, and those gamma rays fly through the apparatus at the speed of light, ignoring magnetic fields entirely, depositing energy wherever they happen to hit matter. Charged pions, on their own clock, live long enough to be steered, but they decay within tens of nanoseconds into muons and neutrinos. Muons are heavier, charged, and similarly steerable for a while, but they also decay into electrons or positrons and more neutrinos. Every step in the decay chain is energy moving away from a useful direction. Sort that mess by what an engine can plausibly use, and you get a smaller number than the original specific energy implied. The charged pions, while they exist, are the prime candidates for thrust. A magnetic nozzle with field lines shaped to push charged particles aft can in principle harvest their momentum. But the timing is brutal. The pions are moving at near light speed, and they have to be redirected before they decay. The geometry has to match. The field strengths have to match. And while you are designing the nozzle to catch the charged pions, the gamma rays from the neutral pions have already left, hitting the inside of the engine bell, the magnets, the structural elements behind, the radiators, the cruise shielding, the avionics. None of those photons turn into thrust. They turn into heat and damage. The decay chain stretches out the loss in time as well. A neutral pion born inside the chamber lives for less than 1/10 of a femtosecond before it disappears into 2 gamma rays. The gamma rays then race outward at the speed of light. A charged pion born in the same event lives about 26 nanoseconds in its own frame, time dilated into a longer life if it is moving relativistically before it decays into a muon and a neutrino. The muon then lives for about 2 microseconds in its own frame, again dilated by motion, before it decays into an electron or positron and 2 more neutrinos. The whole sequence is a cascade of energy carried by ever lighter, ever faster, ever harder to handle particles. Each step deposits a smaller and smaller fraction of the original energy into the engine, and a larger and larger fraction into useless directions. By the time the slowest cascades are complete, much of the original mass energy has already escaped into the universe as photons and neutrinos. The engine never gets a chance to use it. The decay clock outruns the engine clock. The branching ratios make this concrete. CERN's antimatter material lays out the average product distribution from low-energy proton-antiproton annihilation, a little over 1.5 neutral pions per event, about 3 charged pions per event, and small additional branches into other mesons that decay further. Roughly 1/3 of the rest mass energy on each side ends up in neutral pions and then in gamma rays. Another large slice ends up in neutrinos by the time the charged pions and their muon products have decayed. The remaining slice, the kinetic energy of the charged pions during their short lifetimes, is the part the propulsion engineer is actually fighting to capture. That fight is a real piece of engineering, but it is a fight for a slice of the original energy, not the whole pie. There is also an asymmetry the engine never gets to fix. The annihilation reaction does not happen in a single point. The proton and antiproton find each other somewhere inside the chamber volume, at whatever location their trajectories brought them to, and the cascade emanates from that point. If you are firing several annihilations per second, the points form a small cloud. If you are firing many millions per second, the cloud fills the active region of the chamber. The magnetic nozzle has to work for all of those events at once, with each event's products emerging from a slightly different starting position. The field shape that is optimal for one starting point is not optimal for the average over the whole cloud. The nozzle has to compromise. That compromise is one more reason the directed exhaust efficiency falls short of an idealized single-point analysis. So the engineer hands the engine bell a problem it was not designed for, and the problem refuses to be tidied. The original picture was, ignite, point the plume backwards, ride the recoil. The real picture is, stage a cascade, sort which products are still around long enough to steer, accept that a large share of the energy was emitted as gamma rays that already left, and try to extract thrust from what is left. That is why charged pion propulsion is treated, in the propulsion literature, as the cleanest serious thrust channel for an annihilation engine, but never as the whole story. NASA Marshall's overview spells out the bookkeeping. A large fraction of annihilation energy escapes as gamma rays, a further fraction escapes as neutrinos, which interact with normal matter so weakly that they essentially fly through the spaceship and the rest of the solar system untouched. Whatever your nozzle does, those channels are not part of the thrust budget. The maximum effective exhaust speed of an antimatter rocket, when honestly accounted, is well below the speed of light fantasy people often quote. Different concepts put the practical specific impulse in the range of tens of thousands to a few 100,000 seconds, depending on what fraction of the cascade you assume you can use. That is still extraordinary by chemical rocket standards. It is far from the back-of-envelope number you would get by dividing total annihilation energy by total propellant mass. So you do not get the full energy of the fuel as forward thrust. You get the part you can steer on the part of the cascade that lives long enough to be steered, on the directions that intersect your nozzle, on the time you have before the decay chain finishes. Could a clever nozzle at least rescue enough of the good part to matter? That is the question that drove the most serious engineering work in this field, and the answer is honest and bounded. Now stand outside the engine bell and watch a single annihilation event play out across the whole spacecraft. The chamber lights up for a moment. Charged pions head into the magnetic nozzle and contribute a useful kick. Neutral pions vanish almost immediately into pairs of gamma rays, which leave the chamber traveling near the speed of light along whatever directions they happen to be moving when the pions decayed. Some of those gamma rays hit the inside of the engine cavity and deposit their energy there as heat. Others escape through the nozzle throat and the rear of the spacecraft and never come back. Others hit the structure, the radiators, the magnet coils, the shielding. Behind that prompt flash, every charged pion that did not get steered keeps moving. Every muon born from a decayed pion keeps moving. Every neutrino just keeps moving forever through the ship and out into space, carrying its share of energy with it. That is the engine's leak balance. The exact numbers vary with assumptions about the chamber geometry and the magnetic nozzle, but the rough accounting is well established. A substantial fraction of the total annihilation energy, often a large minority, leaves as neutrinos and is lost permanently to the universe. A further large fraction leaves as gamma rays, and only some of those can be intercepted by the spacecraft before they exit. The remainder is divided between the charged pions and their decay products, which is the budget the propulsion engineer actually works with. The fraction that becomes useful directed thrust is a chunk of the original energy, not all of it. The losses are not a rounding error, they are the dominant story. Sit with that. The dream said annihilation converts all the mass into energy with perfect efficiency, and pointed exhaust would convert that energy into thrust. The first half of that statement is true. The second half is the problem. The conversion from raw energy to directed exhaust is where the antimatter ship loses most of its theoretical advantage. The product mix is not a footnote, it is the engine's fundamental boundary. There is one more piece of bookkeeping worth surfacing here, because it shapes the rest of the design. The fraction of energy that leaves as neutrinos is gone for good. No improvement in nozzle design can get it back. Neutrinos interact with normal matter so weakly that no spacecraft of any plausible thickness can intercept any meaningful fraction of them. The neutrino loss is set by the physics of the annihilation reaction itself, so when you read an antimatter propulsion paper that claims an efficiency or a specific impulse, those numbers are built on top of an assumption that the neutrino fraction is already gone. The rest of the engineering, however clever, has nothing to do with that fraction. It is a fact about how the universe distributes the rest mass of a proton-antiproton pair. The spacecraft is allowed to be efficient with what it can reach. It is never allowed to reach the neutrinos. The losses also do not stay clean. The gamma rays that hit the magnet coils heat them. The gamma rays that hit the radiators heat them and stress the materials. The gamma rays that hit electronics cause single-event upsets and long-term degradation. The gamma rays that pass through the crew cause biological damage, which means dose limits, which means more shielding, which means more mass, which means lower performance. Neutrinos do not damage anything, but the energy they carry away is energy that never reached the engine bell at all. The spacecraft sees again and again the same lesson. Energy that does not push the ship still has to be paid for. It is paid for in shielding, in heat rejection, in vehicle margin, and in crew exposure. The cost shows up in places nowhere near the engine. There is also a second leak hidden inside the first. Even the charged pions, the ones the engine is built to use, do not all head obediently aft. They emerge from the annihilation volume in a roughly isotropic distribution, With some bias, depending on the kinematics of the colliding pair, the magnetic nozzle has to turn the forward-going pions around and add them to the aft-going stream, which is a difficult bit of field shaping that costs effort and field strength. Some of those forward-going pions will decay into muons before they can be turned around, and the muons will follow paths the nozzle was not designed for. Some of the aft-going pions will scatter off the field in ways that drop them out of the focused beam. The harvested fraction is always less than the total charged pion fraction, and the total charged pion fraction is always less than the total annihilation energy. Each step is honest. Each step also subtracts. There is also a structural consequence that takes a moment to notice. Because the gamma rays come out in all directions, the spacecraft cannot shield only one direction and call it done. Anything that has line of sight to the annihilation region is exposed. That includes large parts of the engine support structure, parts of the nozzle's own magnet coils, parts of the radiator backing. A real design has to either move those parts out of line of sight, surround them with absorbing material, or accept that they will degrade over the duration of the mission and plan accordingly. Each of those choices costs vehicle mass, vehicle simplicity, or mission lifetime. None of them recovers any thrust. There is one more honesty to add to this picture. Some of the energy that the spacecraft does absorb is energy that the spacecraft wanted to keep moving aft. Gamma rays going backward, in particular, would have been useful momentum if they had only been visible to the nozzle. They are not. Photons of that energy ignore the magnetic field. So the engine pays for the gamma rays twice. Once because they did not become directed thrust, and once because the ones that do hit the back of the spacecraft contribute heat, but not propulsion, on their way out. The net effect is that every gamma ray heading aft and hitting the radiator is energy that the spacecraft had to absorb and then radiate away into space. The same energy could have been part of the exhaust. It was not, because of how it was carried. Then add an honest correction. Real propulsion proposals do not assume perfect collection. They assume the achievable fraction, and they design accordingly. The Marshall overview and the academic literature give a range. The Keen and Zhang beamed core paper, which is one of the most detailed engineering studies of an antimatter rocket nozzle, uses the surviving charged pions as the thrust source and treats the gamma ray and neutrino fractions as lost. Their best case effective exhaust velocity is impressive by any conventional standard, but it does not approach the speed of light. They are working with a knife-edge slice of the original energy. The rest of it has been written off before they begin. That is the right way to read the bookkeeping. The engine concept does not pretend to use everything. It picks a defensible slice and optimizes that slice. The honesty is admirable. The cost is that the headline number on the napkin, the one that justified the entire concept in the first place, has to be cut several times before it lands inside the rocket equation. What kind of engineering could rescue any useful fraction from that mess? Their answer is the next part of the story. Walk around the back of the engine and look at the magnetic nozzle. A beamed core antimatter rocket, in the Keen and Zhang treatment and others like it, replaces the metal expansion bell of a chemical rocket with a region of carefully shaped magnetic field. The annihilation reaction happens at the upstream end of the chamber. Charged pions emerge in all directions. The magnetic field is configured so that charged particles moving generally aft are bent into a focused beam, while charged particles moving generally forward are turned around and added to that aft stream. The neutral products and the gamma rays still escape the way they always do. The job of the nozzle is to do the best possible job with the charged pion fraction. This is not a small piece of engineering. The magnetic field needs to be strong enough to bend relativistic charged particles within the geometry of the engine. That means superconducting magnets capable of producing fields in the tens of Tesla range, operating at cryogenic temperatures, embedded in a structure that is itself being heated by gamma rays from the annihilation. The nozzle has to be optimized so that the pions, which decay within tens of nanoseconds in their own frame, are redirected before too many of them turn into muons that the nozzle was not designed for, and before too many of those muons turn into electrons and positrons and neutrinos that scatter the energy further. The Keen and Zhang paper goes through this optimization in detail. They show that with careful magnetic design and a chamber geometry suited to the angular distribution of the products, you can achieve an effective exhaust speed in the range of about a third the speed of light for the directed pion stream. That is genuinely high. It is not the speed of light, but for spaceflight purposes, it is far above anything chemical or fission could ever offer. It is worth pausing on what a Tesla means in this context. The Earth's magnetic field at the surface is around 50 microtesla, smaller than the field a refrigerator magnet generates at close range. The magnets that bend the Large Hadron Collider's proton beams operate at around 8 Tesla. The strongest sustained continuous magnetic fields ever produced in a laboratory, with superconducting magnets cooled with liquid helium, reach into the tens of Tesla. The Keen and Zhang nozzle design lives in that upper range, with field strengths and field gradients that match the kind of magnet research one normally finds in high-energy physics laboratories, not on spacecraft. Putting such a magnet on a vehicle with all the launch loads, vibration environments, micrometeoroid risks, and thermal cycling that spacecraft are subject to is an engineering problem in its own right. Magnets that work happily inside a stable laboratory have to be redesigned to work in motion, with their cryogenic systems running, possibly while exposed to the radiation field of the very engine they are part of. The nozzle is a physics problem and a full engineering program at the same time. The trade between exhaust speed and thrust shows up in the same paper. Antimatter rockets in this family produce extremely high specific impulse, in the range that translates to effective exhaust speeds well above any conventional engine. They also produce relatively low thrust per kilogram of engine because the mass flow rate is small. A small number of annihilation events per second can deliver an immense amount of energy and produce only a modest amount of momentum because the particles carrying that energy are extremely light. The result is an engine that is wonderful for long-duration burns at low acceleration and difficult to use for a Mars mission profile that wants to accelerate hard, coast, and brake hard. The acceleration phase has to last a long time. The cruise phase has to be short relative to the acceleration phase, which means the engine must keep firing across most of the trip. That in turn means the engine subjects the rest of the spacecraft to its radiation field for most of the trip, rather than for 2 short kicks. So this part of the story is honest. Our magnetic nozzle for charged pions is a real, serious propulsion concept. It is not a placeholder, not a piece of science fiction. It is something engineers can sketch in detail with real numbers, real fields, real materials choices. If the question were only how to extract thrust from the pion stream of an annihilation reaction, you could say there is a viable engineering path. The published designs have specific impulse values that make most other rocket engines look slow. They have plausible chamber geometries. They have plausible magnet specifications. They are not dreams. But step back from the device and look at the rest of the spacecraft, and the rescue narrows. The nozzle solves the local problem of pion steering. It does not solve the loss of gamma rays. It does not solve the loss of neutrinos. It does not solve the radiation field around the engine, which still floods the rest of the ship with photons whenever the reactor fires. It does not solve the storage burden. It does not solve the production scale. It does not solve the heat rejection load. The Keen and Zhang paper is explicit about this. They optimize their nozzle and report the effective exhaust speed they get from charged pions. They do not claim to have solved the full antimatter spacecraft problem. They have solved a piece of it. The rest is left to other studies, and most of those studies have a less optimistic tone. There is also a fact about the published designs that is worth surfacing. They are usually drawn for thrust-to-weight ratios well below 1, sometimes far below 1. That means a beamed core antimatter engine cannot lift off from a planetary surface against gravity. It cannot do quick maneuvering inside a planetary system the way a chemical thruster can. It is, in the propulsion vocabulary, a deep space engine. The ship must be assembled or launched into orbit by some other means, and then the antimatter engine takes it from there. That is consistent with the way other high-specific impulse, low-thrust engines like ion drives are used today on missions like Dawn. It does change the picture of the spacecraft you have to build. A real antimatter ship is launched on chemical rockets, assembled in orbit, fueled with antimatter from some ground facility, and then sent on its way. The engine is half of a system, and the other half is an industrial chain that does not exist yet. That is the right way to read this part of the field. Engine concepts, like the beamed core, are a serious answer to one part of the question. They demonstrate that the engineering imagination has not given up. They also bound quietly how much speed the rest of the ship is allowed to ask for. Even with a successful nozzle, the mission designer still has to live with all the other costs. The shielding is still heavy, the storage is still active, the production is still tiny, the arrival is still mandatory. The crew, where there is one, still has to be kept alive across a burn that may last for months. Even with a better plume, can the ship arrive in any useful state? Return now to the crew and the rest of the spacecraft, and let the engine fire as designed. The magnetic nozzle is doing its job on the charged pions. The radiators are glowing where they should glow. The propulsion is honest, and the rest of the ship is sitting in the radiation field of a continuously running annihilation reactor a short distance away, every second of every burn for the duration of the mission. That field is the same one whose existence the propulsion engineer wrote off as loss. From the propulsion side, gamma rays and neutrinos that do not contribute to thrust are simply gone. From the spacecraft side, those gamma rays are still inside the vehicle. The gamma ray dose at any nearby location near a high-power annihilation engine is severe. Calculations in the radiation literature for relativistic and near-relativistic propulsion concepts make this concrete. A 2004.10079 study of radiation conditions in relativistic interstellar flight does the math for crews and instruments aboard fast spacecraft, including those driven by exotic propulsion. The conclusion is consistent across studies. The internal gamma-ray field around the engine of a working antimatter rocket would, without serious mitigation, exceed safe dose limits for crew and damage limits for electronics within timescales that are short compared with mission length. The dose problem is not theoretical. It is already a working assumption inside the propulsion community. You can solve part of that with shielding. The standard tools are well known. A dense material like tungsten or depleted uranium is good at attenuating gamma rays per unit mass. Hydrogen-rich materials are useful for neutron capture in any concept that produces neutrons. Water or polyethylene tanks can serve double duty as both consumables and shielding. You can also solve part of it with distance. Gamma-ray dose drops at least linearly with distance and faster than linearly when you account for absorption in intervening structure. So a typical antimatter spacecraft design puts the engine on the end of a long boom, with the crew compartment many tens of meters away at the other end, and a shadow shield in between sized to absorb most of the prompt gamma flux from the engine direction. The shadow shield is shaped like a thick disc, with the engine on one side and the rest of the ship in the cone behind it. That solves the worst-case dose. It does not come free. The boom is mass, the shadow shield is mass, the redundant shielding around the crew is mass, the water you carry for drinking and cooling is mass, the avionics shielding is mass. Even when each individual mass is small, they add up. The Marshall Overview and other propulsion studies are explicit that the practical performance of an antimatter rocket falls when you account for the radiation-driven structural requirements. A nominally compact ship becomes long, with a small engine module at one end, a long structural truss in the middle, and a small habitat module at the other end, with shielding and radiators distributed along the truss. The image you started with, a sleek engine pushing a small crew capsule, becomes harder to draw without admitting how much of the vehicle is now boom, shield, and radiator. Even the way that shielding works is not as simple as a wall thickness. Gamma rays of different energies attenuate at different rates in different materials. A few centimeters of tungsten can stop a mega-electron volt class gamma ray to within an acceptable fraction of its original intensity, but the energy spectrum of annihilation gammas spans a wide range, with some lines well above the easy-to-stop band. Some of those gammas pair-produce inside the shield itself, creating electron-positron pairs that then scatter further, producing secondary photons and electrons that have to be absorbed by the rest of the shield. The shield is therefore not a passive plate. It is a cascade-absorbing structure whose own performance depends on the spectrum of the radiation hitting it and the geometry of the engine behind it. A shield built for one engine power level may not work for another. A shield built for one geometry may not work after a hardware change. The shielding decisions are tied to the engine design, which is tied to the mission profile, which is tied to the spacecraft architecture, all the way down. There is no clean separation between the propulsion engineer and the shielding engineer in a real antimatter spacecraft. They are designing the same machine. That habitat module also stops being a generous space. To minimize the mass of the human compartment that has to be shielded, designers shrink it. Volumes that would have been comfortable for a long, crewed mission shrink to the minimum because every cubic meter inside the shadow shield costs shielded mass elsewhere. Electronics are clustered into hardened cores. Robotics are preferred over crew where possible because robots can tolerate higher cumulative doses without dying. The longer the burn, the more aggressively the design slides toward compact, hardened and partially robotic. Sleeping quarters become bunks. Storage becomes shelving along the inside of the shielded wall. Privacy becomes a curtain. The trade is not aesthetic, it is structural. You can also see the consequence in the failure modes. A boom that is many tens of meters long has to survive launch, deployment, and the thrust loads of the engine. It has to remain straight enough to keep the shadow shield in the right place. A shadow shield that fails to track the engine direction lets gamma rays around the edge into the crew compartment. So the structure has to be stiffer than a typical thin-walled spacecraft truss with attitude control that keeps the entire long stick pointed correctly. That is more mass. That is more complexity. That is more places where something can break in a mission where almost nothing is allowed to break. There is also a more subtle hazard that lives at the edges of the shadow. A shadow shield blocks photons traveling along a narrow cone from the engine. Photons traveling along directions outside that cone, even slightly outside, can leak past the shield and reach the crew compartment by scattering off the structure or off the residual gas in the spacecraft. So the geometry has to be checked carefully for indirect paths. A pipe that runs from the engine area into the habitat carries radiation along with whatever fluid it carries. A truss member that connects the two ends of the ship offers a path for scattered photons. Even the radiator surfaces, if they extend back into line of sight of the engine, can become secondary sources. The shielding design, therefore, involves not only the main shadow shield, but a careful accounting of every line of sight from the engine region to anything alive or delicate elsewhere. The crew compartment ends up partly shielded by the rest of the ship, with a careful map of where photons can and cannot reach. What you end up with in the honest design space is a spacecraft whose proportions are not chosen by aesthetics or convenience, but by the physics of what the engine is throwing at the rest of the vehicle. The propulsion forces a habitat geometry. The habitat geometry forces a payload limit. The payload limit forces what kind of mission you can fly. Antimatter changes the ship before it changes the schedule. It tells you what kind of vehicle you are allowed to build. Now follow the energy that did not become thrust and did not leave cleanly through the back. Look at the gamma rays that hit the engine bell and the magnet coils. Look at the muons and electrons and positrons that scatter into the structural elements. Look at the neutrons in any concept that produces them. Look at the damaged electronics and the heated shielding. All of that energy lives inside the vehicle now, and the vehicle has to deal with it. There is no surplus heat sink. Every bit of energy that did not become thrust and did not leave as a neutrino has to be radiated away from the spacecraft's outer surface as infrared light. In space, the only way to lose energy is to radiate it. There is no air to convect heat into, no ocean to dump it into, no atmosphere to disperse it through. Every joule that enters the spacecraft as heat must leave the spacecraft as radiation from a surface, and that surface must be hot enough and large enough to push the heat out faster than the engine puts it in. The relationship between heat power, surface area, and surface temperature is set by the Stefan-Boltzmann law and is unforgiving. To reject power at a given temperature, you need surface area in proportion. To reject more power at the same temperature, you need more surface area. To reject the same power at a lower temperature, you need a lot more surface area. because the radiated power scales as the fourth power of temperature. For an antimatter engine that absorbs a large fraction of its own gamma rays in shielding and structure, the heat rejection requirement can be large. Even a fraction of a megawatt of waste heat requires square meters of radiator at moderate temperatures, and the practical operating temperatures of large structural radiators are far below the surface of a fission core or a re-entry shield. So the radiators on a serious antimatter ship grow into large structures, panels stretched along the truss, deployable surfaces, fins that catch starlight on one side and pour infrared into space on the other. Those panels are mass. They are mechanical. They have to survive the radiation field and the thermal cycles of the burn. They have to fold for launch and unfold reliably for the cruise. Every joint in the deployment system is a place where something can fail. This is the part of the story where the compact engine fantasy dies most visibly. You came in expecting a ship that was small because it carried so little fuel. The engine itself, with its magnetic nozzle, may still be reasonably compact. The propellant tank by mass is small, but around the engine grow the support systems. Around the crew grow the shielding. Along the truss grow the radiators. Around the avionics grow the hardened enclosures. The ship is no longer small. It is long, sparse in the middle, busy at both ends, and engineered everywhere to survive the very engine it is built around. The radiator material enters the same accounting. A radiator surface has to have a high emissivity in the infrared band where most of the waste heat leaves, and a low absorptivity in the visible band where sunlight could pour energy back into the ship. It has to survive the radiation environment of the engine without losing those optical properties. It has to be light enough that the rocket equation does not eat the performance margin. It has to be repairable in flight, because a meteoroid or a thermal cycle failure can puncture a panel and force the mission to either patch it or accept reduced thermal capacity. Heat pipes and pumped fluid loops have to move the absorbed energy from the engine and shield regions out to the radiators, which means more plumbing, more pumps, more fluid mass, and more places for a leak. Each piece is a small engineering problem. Together, the heat rejection chain becomes a major fraction of the spacecraft's complexity and a substantial fraction of its mass. The waste energy budget shapes the ship's body almost as much as the thrust budget does. It is also worth keeping in mind that the heat does not have to be rejected uniformly along the truss. Some designs in the literature cluster the radiators near the engine, where the gamma ray heating is highest, and let the rest of the structure stay cooler. Other designs spread the radiators across the full length of the truss to give the engine a longer time-averaged thermal load. The choice depends on the engine's burn profile, the available radiator materials, and the structural loads the truss can carry. None of those choices is free. Each adds complication. The radiator design problem is, by itself, the kind of problem that a whole spacecraft engineering team can spend a year on before any of the other subsystems are designed. There is a quiet feedback effect that makes this worse. Bigger radiators mean more radiator mass. More radiator mass means the engine has to push harder to accelerate that mass. Pushing harder means more annihilation events per second. More annihilation events per second means more gamma flux. More gamma flux means more heat absorbed in the structure. More heat absorbed in the structure means bigger radiators. Round and round it goes until the design finds an equilibrium where every part is sized for every other part. The equilibrium ship is bigger and slower than the back of envelope ship. The size penalty is not a small correction. It is the central engineering result of taking the heat problem seriously. That changed character is also part of the answer to the question of how much speed you actually get. The published mission studies that take heat and shielding seriously end up with vehicle masses that are not as small as the propellant comparison alone would suggest. They are smaller than chemical rocket equivalents, but the savings are not the orders of magnitude that the energy density would imply. The mass budget is dominated by the survival systems, not the fuel. The propellant fraction is small. The systems fraction is large. The ratio between them looks much more like a deep space probe with a heavy power system than like a clean compact rocket. There is also a quieter mass term that the literature does not always name explicitly. The active control systems for the trap, the engine, the shielding, and the radiators all need power. That power comes from a power system, which is itself mass. The crew needs life support, which is mass. The mission needs communications hardware able to reach Earth across the propulsion radiation environment, which is mass. The mission needs navigation hardware able to function in the field, which is mass. Each of those is small individually. The total can easily be a substantial fraction of the dry mass of the ship, and every kilogram of dry mass is, in the rocket equation, a kilogram that has to be accelerated and braked by the propulsion system, which means more annihilation events, which means more gamma flux, which means more shielding, which means more dry mass. The system is coupled at every joint. There is no clean way to optimize one piece in isolation. Once that is on the table, you can see why the design cannot simply add power and keep winning. Every extra unit of engine power pushes the radiator size, the shield mass, the boom length, the trap power draw, all upward. There are diminishing returns. There is an optimum somewhere, and above that optimum the ship gets worse, not better. The compact miracle picture is incomplete. The honest picture is a ship that is genuinely faster than chemical alternatives, but not as much faster as the textbook fuel comparison alone would predict, and built with a vehicle scale and complexity that look more like a nuclear submarine in space than a sleek interceptor. If the vehicle keeps growing just to manage itself, what happens when it also has to slow down? Up to now, the imagined trip has been an outbound dash. Burn hard, build velocity, coast, arrive. Except that arriving is the part of the trip the mission was funded for. Whatever the science target is at the far end, it usually wants the spacecraft to slow down, swing into orbit and operate, not blow by at relativistic speed and send a postcard. The moment you ask for that, the propulsion balance changes again. A flyby that lasts hours at the target body is a poor return on a mission that took months or years to fly. The instruments cannot collect enough data, the cameras cannot dwell on enough features, the communications cannot send back enough samples. The mission is essentially over before it begins. There is a clean version of the rocket equation that comes up in this kind of conversation. The total propellant mass needed scales exponentially with the velocity change the spacecraft needs to perform, divided by the effective exhaust speed of the engine. Once you have an effective exhaust speed in the range of tens of thousands to hundreds of thousands of seconds of specific impulse, the propellant mass for a one-way change in velocity becomes manageable. But the moment the mission asks for two changes in velocity, one to accelerate and one to brake, the propellant cost goes up, often by a factor of more than 2, because the ship has to carry the braking propellant during the outbound burn. NASA's deceleration of interstellar spacecraft work is concerned with exactly this. They study how to make a fast probe slow down at the destination, and they note that even with antimatter, the architecture of the mission changes if arrival is mandatory. The NIAC deceleration study and the broader literature look at several options. One is a magnetic sail that catches the interstellar medium to brake. One is a separate deceleration stage that fires antimatter the other way at the end of the trip. One is a slower cruise that gives the spacecraft more time to decelerate over a longer arc. One is a gravity assist at the target system, where the spacecraft swings past a body to lose velocity, though that only works for certain destinations and asks for very precise trajectory work. None of them are free. Each makes the vehicle more complex, heavier, or longer in transit. There is no architecture in the literature where a pure antimatter rocket gives you the full theoretical speed advantage on outbound, then arrives at its destination in usable condition without paying somewhere on the back end. Apply that to the Mars mission you started with. Mars is far away, but not so far that arrival cost is overwhelming, because Mars has gravity and an atmosphere that can help. Even so, the mission has to insert the crew into orbit, descend to the surface, ascend back to orbit, and return to Earth. Each of those phases is a velocity change. Each carries propellant mass. Apply it to a deep space target instead, like an outer planet or interstellar precursor mission, and the asymmetry becomes brutal. The destination has no convenient atmosphere or magnetic field of the right kind to brake against. The deceleration must be done by the engine, which means another long burn at the far end, which means another propellant inventory carried for that burn, and another period of the engine throwing radiation into the spacecraft. There is also a curious feature of antimatter braking that does not appear with chemical engines. Some of the deceleration concepts in the literature involve firing the antimatter engine forward, throwing exhaust ahead of the spacecraft to slow it down. With chemical rockets, this is just a matter of turning the ship around and burning. With an antimatter rocket aimed forward, however, the engine's gamma-ray field washes into the front of the spacecraft instead of the back. The crew compartment, if there is one, sits behind the engine during outbound burn and in front of the engine during braking. That changes the shielding geometry. It changes the truss design. It may require either a second shadow shield on the other side of the crew compartment, or a careful rotation of the entire ship to keep the crew in the protected cone. None of that is impossible. It does mean the spacecraft is not the same in both directions, and the design has to account for both phases honestly. Mission planners cannot pretend this away. Even if the engine is the same antimatter rocket, the mission profile changes the math. A flyby probe is easier than an orbiter. An orbiter is easier than a lander. A lander that has to return to Earth is harder than a lander that stays. Every step that adds a useful science capability adds a velocity change, and every velocity change multiplies the propellant cost. Each multiplication means more time in the antimatter field, more shielding, more storage hardware, more wear and tear, more failure paths. The rocket equation has a subtler tax in it too. Carrying braking propellant means accelerating that propellant during the outbound burn, which means the engine has to push harder than it would for a one-way mission of the same outbound speed. Pushing harder means burning more propellant. Burning more propellant means carrying still more braking propellant, since you do not want to arrive without a way to slow down. The recursion only converges because of the high specific impulse of an antimatter engine. With a chemical engine, the recursion blows up and no mission of this kind is feasible at all. With antimatter, the recursion converges, but it converges at a vehicle mass much larger than the one-way analog. Mission designers sometimes call this the staging penalty, though here it appears even without literal stage drops, because the entire spacecraft is carrying its arrival propellant as embedded mass throughout the outbound trip. There is also a less obvious mission cost. The acceleration phase of an antimatter ship is long. The braking phase is also long. The middle, where the spacecraft is coasting at high velocity with the engine cold, is short relative to the burns, so the crew spends most of the trip inside an active engine field on either the outbound or the inbound burn. The radiation exposure is not a brief penalty during ignition. It is a sustained dose across the working part of the mission. Shielding has to be sized accordingly. Communication and operations have to be planned around an engine that is almost always firing. There is one strategy that gets some attention in the literature, called magnetic sail braking, where the spacecraft deploys a large loop of superconducting wire and uses the interaction between that loop and the interstellar magnetic field or the solar wind to slow itself down. The interaction is weak per unit area, so the sail has to be enormous. It also only works in regions where there is enough plasma to push against, which is fine for some destinations and useless for others. For a Mars mission, there is no relevant interstellar medium to push on. For a deep space precursor, a magnetic sail can shave some velocity off the cruise without spending propellant, which is a real engineering win, but it does not eliminate the need for a final braking burn at the target. So the strategy reduces the antimatter braking budget without removing it. Like most of the workarounds in this field, it is a partial answer. That is why serious antimatter mission studies, when they look at where the propulsion makes the strongest case, often drift toward missions where the cargo can absorb a tough arrival. A small interstellar probe that needs to do something at the far end can sometimes accept a brutal deceleration. A flyby of a distant body, where a few minutes near the target are good enough, may be acceptable. But a crewed Mars round trip, with all the comfort and reliability margins humans need, asks for full mission architecture, full reusability of the propulsion at both ends, full vehicle survivability. The propellant savings from antimatter's energy density start to look less generous when you have to carry enough of it to brake, turn around, and come back. Does the popular Mars version still make sense after all of that full mission accounting? Time to revisit it head-on. Step back to the Mars ship from the opening, but redraw it with everything tonight's argument has added. The propellant tank has shrunk in mass. In its place sits a Penning-class trap with superconducting magnets, vacuum systems, and continuous power draw. Behind the trap is the annihilation chamber and the magnetic nozzle of the beamed core engine. Behind that, the gamma-ray field of the chamber stretches out, attenuated by a shadow shield. Behind the shadow shield, on a long structural truss, sit the radiators and the avionics enclosures. At the far end of the truss is the crew habitat, smaller now than the chemical era design imagined, hardened against gammas and against the cosmic background that any deep space ship lives in. The propellant for braking sits in another trap further along, ready for the arrival burn at Mars. The propellant for the return trip sits behind that, with its own confinement hardware and its own active control. Every part of the ship is there for a reason that has nothing to do with going to Mars in particular. The trap is there because antimatter cannot sit in a tank. The shield is there because the engine throws gammas at the crew. The radiators are there because absorbed energy has to leave. The truss is there because shielding works partly through distance. The hardened avionics are there because electronics fail in radiation. The compact habitat is there because shielded volume is expensive. Mars, as a destination, did not ask for any of this. The engine did. None of it is unique to the route between Earth and Mars. The same hardware would be there for a robotic flyby of a distant body, for a deep space precursor, for an interstellar probe. The destination is incidental to the architecture. The crew amplifies all of it. Robots can be designed to tolerate higher cumulative doses and recover from single event upsets. Humans cannot. The dose limits for a crewed mission are set by lifetime exposure to ionizing radiation, with constraints from agencies like NASA on cancer risk, central nervous system effects, and acute exposure. The internal field of an antimatter engine, even with shielding, pushes those limits hard. Every extra meter of standoff distance helps the dose math. Every extra centimeter of shield helps the dose math. Every extra hour of cruise time hurts it. The mission planner faces a trade where the propulsion that was supposed to shorten the dose by shortening the trip is itself a dose source for the entire duration of the burn. The two pressures fight inside the same design. There are also reliability questions that do not show up in the propulsion datasheet, but dominate human-rated programs. The Apollo program lost 3 astronauts on the pad, and almost lost 3 more in the Apollo 13 oxygen tank failure on the way to the Moon. The Space Shuttle program lost 2 crews in flight. Long-duration human spaceflight, even at its current modest reach, has cost lives because spacecraft are complex and failure paths are many. An antimatter ship adds new failure paths that no human spacecraft has ever flown with. Each new failure path has to be characterized, tested, and made safe enough that a crew can be put on top of it. The certification of a new propulsion technology for human spaceflight, even an old and well-understood one, takes years. The certification of an antimatter propulsion system, with all the unknowns it would carry, would likely take decades and involve many uncrewed test missions before any human-rated launch was contemplated. None of that history fits inside a short development timeline. There is a long surface stay folded into the Mars mission as well. Even with a fast outbound transit, the orbits of Earth and Mars line up for a return trip only every 26 months or so. Either the crew waits on the surface for the next launch window, or the mission carries propellant for a less efficient return arc that does not follow the standard Hopman economy. With antimatter, the second option becomes more thinkable than it would otherwise be, but it asks the trap and the engine to wait, cold or warm, for a long time at Mars, ready to fire again, with all the storage burdens still active. The mission timeline is longer than the engine's burn time by an enormous factor. The trap has to remain alive across that whole interval. The cryogenic systems have to keep running. The vacuum has to hold. The control electronics have to remain alive. None of that fits a quick interplanetary sprint. Then there is the question of what happens if something goes wrong. A chemical rocket that loses its engine on the way to Mars is bad news. An antimatter ship that loses its trap on the way to Mars is much worse. Lose magnetic confinement and you release the entire stored antimatter inventory at once. in an annihilation event that turns whatever fraction of the fuel is annihilating into a burst of energy comparable, in raw terms, to a small nuclear yield. The spacecraft is dead, and anything nearby is in danger too. That places a reliability requirement on the trap system that is harder than reliability requirements anywhere else on a normal spacecraft. The trap cannot fail, the control loop cannot fail, the power supply cannot fail. There must be multiple redundant systems, each of which is also mass, also complexity, also a possible failure path. There is also the practical question of where the antimatter for a Mars mission would come from. Even granted a future where dedicated production has scaled enormously, the rate of production sets the rate at which missions can be flown. If producing milligrams of antimatter takes years even in an optimistic future scenario, then a crewed Mars campaign that needs propellant for outbound braking, surface stay and return cannot launch faster than the production rate allows. The cadence of human Mars exploration would be tied to the cadence of a factory unlike any humans have built. That coupling shows up nowhere in the popular pitch, but it is a real constraint. The mission is expensive in mass and expensive in scheduling. A program that builds one ship and waits a decade for its propellant is not a program that fits political timescales easily. In that design space, Mars stops being the easy sales pitch and becomes the case that exposes the burdens most clearly. The mission is hard not because Mars is far. It is hard because a crewed antimatter ship has to solve everything tonight has named in the worst configuration, with no robotic margin and no acceptance of catastrophic failure. The Mars architecture is the hardest place to be optimistic about pure antimatter propulsion, not because the physics gets worse, but because the mission asks for everything at once. That does not make Mars impossible. Engineering history is full of architectures that looked impossible from a distance and turned out to be a long climb rather than a wall. It does mean that the popular sales pitch where antimatter trivially cuts Mars trip time and the crew strolls out a year later is not honest with the rest of the design. The bounded answer is that antimatter changes the propulsion math while everything else gets harder, and the mission profile where humans benefit most is also the one where the cost is highest. If humans make the case harder, which missions actually gain the most from antimatter? Take the crew out of the ship and let the same architecture do a different job. The trap is still there, the engine is still there, the shielding is still there in a smaller form, sized for electronics rather than for crew. The truss is still there but can be shorter, because the standoff distance no longer has to protect human bone marrow. The habitat is gone. In its place is a smaller payload module with instruments, batteries, communications hardware, and possibly a small lander or rendezvous package. The radiator burden is similar. The trap burden is similar. The production and storage burdens are still there. But the mission can absorb dose levels that would be unacceptable for a crew. That single change reshapes which missions look reasonable. A robotic precursor mission to the outer solar system, or an interstellar precursor mission to a few hundred or a few thousand astronomical units out, runs on years of cruise time. The propellant savings from antimatter's energy density start to matter more, because the propellant fraction of a chemical mission to those distances is hopeless. The dose limits relax. The mission can be optimized for raw delta-V and arrival science, not for human comfort. The roadmap to interstellar flight from NASA-affiliated authors discusses concept lanes for missions like these, including those driven by antimatter assist or by other exotic propulsion. The deceleration study from NIAC works in roughly this regime. The mission target is not a person on Mars in 2 years. It is a science package at a far destination on a decadal timescale. The dose advantage for an uncrewed ship is real, but only partial. Modern spacecraft electronics are radiation hardened to survive doses in the kilorad to megarad range, depending on the part. That is several orders of magnitude above what a human can survive. So the same radiation field that would force a crude antimatter ship into long booms and heavy shields can sometimes be accepted by a robotic ship at much closer range. The truss can shrink, the shadow shield can shrink, the boom mass can fall. Some of those savings can be reinvested in propellant or in instruments. The robotic ship is, in the end, the same architecture pared down to the level of damage a chip can take instead of the level a body can take. That is a real engineering win, even though it does not change the production base or the storage requirements. There are concrete examples in the literature. Voyager-class probes are still active decades after launch on chemical propulsion. New Horizons reached Pluto in 9 years with a launch boost from Earth and 1 gravity assist to go meaningfully farther into the interstellar medium and out to bodies like potential Planet 9 or to nearby star systems. You need either decades of patient crews or a propulsion technology that can deliver speeds those chemical-era probes cannot. Antimatter, even in concept form, is on the short list of technologies that could in principle deliver a probe to the heliopause or beyond in a single human lifetime. The Interstellar Roadmap puts that ambition on the table, with antimatter listed as one of the candidate propulsion families. There is a useful detail in some of the deep space concepts that does not get much press. Several proposals build the antimatter ship in 2 pieces, a power and propulsion module that produces and uses the annihilation reaction, and a science package that hangs off the front. The science package can be relatively simple with hardened electronics, a few instruments, and a communications dish. The propulsion package can be relatively complex with traps and shields and radiators optimized for one job. Because they are separate, the science package can be designed to a different reliability standard than the propulsion package, which simplifies certification of the whole vehicle. That kind of architectural split is hard to do on a crewed ship, where the crew compartment has to be carried along the entire trip and cannot be discarded after acceleration. For a probe, the modular split is one more reason robotic missions look more natural in this regime. Even there, the architecture problem does not go away. The production scale is still the same. The storage system is still active. The radiation field is still hostile to electronics. The arrival problem is, if anything, sharper, because the destination is farther and the relative velocities are higher. You do not remove the burdens by removing the crew. You remove the constraint that says all the burdens must stay below human survivability. With that constraint loosened, the optimization can push toward higher engine power, higher velocity, smaller payloads, faster trips, and more aggressive heat rejection. Many of the most serious mission studies that include antimatter, including the deceleration work and the broader interstellar roadmap, live in this regime. There is a planning idea sometimes called a precursor mission that helps clarify why distance pays. A precursor probe is one that goes ahead of any larger mission and answers questions that the larger mission cannot answer from Earth. For interstellar travel, an antimatter-driven precursor might be a probe that reaches the heliopause in a few decades rather than a few centuries, or that flies to a nearby star system in a human lifetime rather than across many human lifetimes, sending back data the rest of the field can use to plan whether to build anything bigger. The precursor does not have to do everything. It just has to go far enough and fast enough to be unique. That is the sort of role antimatter could fill if its production and storage problems were partially solved. Even small steps in those problems would open up missions that no other propulsion concept could attempt. That is also where the rhetoric quiets down. Robotic deep space missions do not sell as easily as crewed Mars. They are smaller. They are slower in the political clock. They do not put a face on television. But they are also where the math is honest. If antimatter has a defensible mission lane in the foreseeable future, it is more likely a robotic probe doing something a chemical or nuclear concept cannot than a fast Mars crew transfer. The science return per kilogram of antimatter is higher when the kilogram of antimatter goes farther. The cost of carrying everything an antimatter ship needs is amortized across a more demanding destination. The trade pulls the technology toward distance. There is a temptation to leap from that observation to a confident future. Resist it for a moment, because the institutional view inside the propulsion community is more careful. NASA's interstellar roadmap is explicit that no current technological ladder reaches antimatter-class propulsion. The deceleration paper does its math for missions that no agency has funded. The body of work is taken seriously as a long-horizon question, not as a near-term development plan. Distance from Earth raises the reward, but the production gap, the storage burden, the radiation costs, and the heat rejection problem are still there at the same level they always were. The probe still needs the propellant, The propellant still needs the trap. The trap still needs the power. None of that is solved by sending the mission farther. If the farthest missions make the best emotional case, what does the serious near-term field do instead? It retreats from purity. The retreat is not embarrassment. It is a scientific judgment about which version of the antimatter problem can actually move forward in a human generation. The clearest example is the NASA concept for radioisotope positron propulsion, sometimes called RPS antimatter or the positron catalyzed concept. The idea is straightforward. Instead of using antimatter as the dominant energy source, use it as a tiny ignition trigger. Tiny amounts of positrons, produced from a radioisotope on board, annihilate with electrons in a chamber and provide the heat or radiation needed to start a more conventional propulsive reaction, such as a controlled fission or fusion event in a small fuel pellet. The bulk of the energy comes from that secondary reaction. The antimatter just lights the fire. This shift is doing several useful things at once. It dodges the production problem, because the amount of antimatter required falls by many orders of magnitude. It dodges the storage problem to roughly the same degree, because a much smaller trap is easier to keep alive. It dodges the radiation field problem, partly because a smaller annihilation rate produces a smaller flux of gamma rays. It dodges the heat rejection problem in proportion, and it lets the propellant deliver thrust in a chemistry or physics where mass flow is large, which improves thrust to weight and makes for less awkward mission architectures. The acceleration phase no longer has to be a months-long slow burn. The mission can fire harder for shorter intervals and coast through the middle the way a more conventional design would. The medical analogy is closer than it sounds. Hospitals already use positron emission tomography, where a small amount of a positron-emitting isotope is injected into a patient, and the gamma rays from the resulting positron-electron annihilations are imaged to map metabolic activity. The isotopes used are produced in dedicated facilities, transported quickly because of short half-lives, and used within hours. The infrastructure to produce and handle medically useful positron sources is well established. A small trigger propulsion concept does not need to invent positron handling from scratch. It can build on an existing base, scale it up, harden the systems for spaceflight, and design the trigger geometry to match a fission or fusion target. And none of that is easy, but it is closer to a continuous development path than the pure annihilation concept, which still asks the world to invent antiproton production at a scale the world has never approached. Schmidt and colleagues in the late 1990s and early 2000s wrote one of the clearest comparisons. Their paper compares antimatter requirements for several near-term applications, including pure annihilation propulsion, antiproton catalyzed microfission, and antiproton catalyzed inertial confinement fusion. The pure annihilation cases ask for milligrams to grams of antiprotons. The catalyzed concepts ask for nanograms to micrograms. That is a difference of 6 to 9 orders of magnitude in antimatter inventory. Their conclusion is straightforward. With realistic projections of antiproton production capacity, the catalyzed concepts are far more plausible in the foreseeable future than the pure annihilation concepts. The bottleneck moves from antimatter production to the conventional propulsion physics surrounding it, which is also hard but already inside the historical engineering experience of fission and fusion programs. There is a subtle thing happening here. The field has, in effect, looked at the propulsion problem honestly, and chosen to use antimatter as a small ignition trigger inside a larger conventional reaction, rather than as the main fuel in its own right. That is a quiet but important admission. The dream of an antimatter rocket as the primary energy source for a starship is held at arm's length, while the more pragmatic dream of antimatter as an ignition mechanism is brought closer. The two concepts look superficially similar on a poster. They are very different on a balance sheet. One asks the world to produce milligrams of stored antimatter. The other asks the world to produce nanograms, in much the way medical positron emission imaging already uses small amounts of antimatter routinely. The catalyzed concept also benefits from a clear emission profile. A pure annihilation drive needs a long, continuous, low-thrust burn that exposes the spacecraft to its own radiation field for months. A catalyzed concept can use shorter, harder burns separated by long coasting periods, with the engine off for most of the trip. That difference in burn profile changes shielding requirements, changes thermal cycles, and changes crew exposure. None of those changes are small. That is also why some popular discussions blur the line. A press release that talks about an antimatter rocket can mean either a concept that burns antimatter as its main energy source, or a concept that uses a small antimatter trigger to ignite something else. The two share a vocabulary. They do not share an architecture. Honest treatments of the field, including NASA's own materials, distinguish them carefully because conflating them inflates the readiness of the more demanding concept. A catalyzed fusion design with a positron trigger is not on the same readiness ladder as a pure annihilation drive. Both can be called antimatter propulsion in casual speech. Only one of them has a path through current production and storage technology. There is also a less heroic reason the field has moved in this direction, and it is worth saying plainly. The funding for propulsion research at agency scale rewards concepts that have a plausible development path within a planning horizon that funders can defend. A concept that may pay off in a century is hard to keep funded across electoral cycles. A concept that uses a small amount of antimatter to ignite a fission or fusion reaction has a near-term plausibility argument. The antimatter quantity is already in the medical range. The propulsion physics is already partly understood from nuclear weapons design and fusion research, and the engineering steps from paper concept to small test article are imaginable on a decadal timescale. That is fundable in a way that a pure annihilation rocket simply is not. The field, in choosing where to spend its work, is also responding to the incentives of how its work is funded. That is not a complaint. It is just one more reason the hybrid lane has become the more populated one. The catalyzed concepts also have a useful side property. They degrade gracefully. If the antimatter quantity on board is smaller than planned, or the trap loses some of its inventory during the cruise, the spacecraft can still propel itself with a slightly reduced number of ignition events. The mission does not fail catastrophically because some of the fuel has decayed away. With a pure annihilation rocket, losing a fraction of the propellant means losing a corresponding fraction of the mission's delta-V capability. With a catalyzed concept, the trigger amount is small enough that the spacecraft can sometimes still complete its mission on the conventional propellant alone, at the cost of a longer arrival time or a smaller payload. Robustness against fuel loss is not a flashy property. It is a real one, and it tilts the balance further toward the hybrid lane for any mission where graceful degradation matters more than peak performance. You can read the hybrid retreat as a defeat for the original dream, or you can read it as the field doing what good science always does, which is to find the part of the question that can actually move and pour the work there. The pure annihilation rocket remains scientifically serious as a limit case. The catalyzed concepts remain scientifically serious as a near-term research lane. The two together draw a map of what the energy density of antimatter is actually buying. It is buying a small set of catalyzed propulsion concepts that may, with continued work, become real. It is also buying a sharper picture of why the pure version stays out of reach. After all of these retreats and workarounds, what does antimatter honestly buy us? Pull the camera all the way back. The ship from the opening is still there, suspended in a slow planetary orbit. The route to Mars still drawn across the cabin display. The propellant tanks have been replaced in the engineer's blueprint by a Penning-class trap with superconducting magnets, cryogenic cooling and redundant power. The engine bell has been replaced by a magnetic nozzle. The structural truss has stretched to put the engine far from the crew. The shielding has thickened. The radiators have grown. The avionics have hardened. The crew habitat has shrunk. The braking stage propellant sits in a second trap. The return stage propellant sits in a third. Every change follows from a physical problem we already walked through. None of it makes the spacecraft simpler. That is the practical answer once the numbers are written down. Antimatter has enough raw energy to support deep space propulsion on paper. The trouble is the rest of the vehicle. Production is still far below mission scale. Storage is an active machine that has to stay alive for the whole mission. Annihilation does not give you a clean exhaust stream. It gives you a particle spray with gamma rays and neutrinos carrying away much of the energy and only a fraction of the charged particles available for thrust. Shielding becomes layout. Heat rejection becomes mass. Braking at the far end repeats the same burden a second time. By the end of the accounting, the simple miracle rocket is gone. That does not make the concept useless. It narrows where it is useful. The clearest near-term lane in the literature is the catalyzed one, where a tiny amount of antimatter triggers a much larger fission or fusion event that cuts the storage problem down from mission fuel to ignition supply. It also means the rest of the propulsion system can be built around propellants and reactor hardware that engineers already know how to discuss in more realistic terms. The antimatter stays important, but it stops carrying the full mission alone. Pure annihilation propulsion stays in a different category. It is still worth studying because it sets the far edge of the problem. If you want to know how much a propulsion concept can gain from fuel energy density, antimatter gives the extreme case. The studies are useful for that reason. They show what breaks first. They show how quickly shielding, cooling, storage, and reliability take over the design. They show that a vehicle can have extraordinary fuel energy and still end up slow, fragile, and heavy once the whole mission is counted honestly. The timeline follows from that. Ion engines had a much easier underlying technology base and still took decades to become routine flight hardware. Nuclear thermal propulsion reached ground testing and still has not flown an operational mission. Fusion propulsion has been studied for years without becoming a spacecraft program. Antimatter propulsion starts farther back than any of those. That does not make it fake. It does make it distant. There is a mission design consequence hidden inside that timeline. Programs do not invest in propulsion in the abstract. They invest because the vehicle closes a mission that cheaper systems cannot close. For a crewed Mars flight, that closure test is severe. The ship has to leave Earth orbit, cruise for months, brake at Mars, protect a living crew during the transfer, wait out the surface stay, and then repeat the trip home. A pure antimatter ship does not get credit for its raw energy unless it can do all of those jobs with lower total mission burden than nuclear thermal, solar electric cargo support, chemical staging, or some hybrid combination. Once you state the comparison that way, the burden shifts away from the fuel headline and back onto the whole spacecraft. That is also where robotic missions start to look more favorable than crewed ones. Remove the crew and several design pressures soften immediately. The habitat can disappear. The life support mass can disappear. Some of the shielding can be reduced because the cargo does not care about dose in the way a human body does. The acceleration profile can be tuned entirely around the payload and the engine, not around crew tolerance or surface stay timing. A deep space robotic science mission that needs extreme delta V is still a hard case for antimatter, but it is a cleaner case than a crewed Mars transport. The literature repeatedly drifts in that direction for a reason. The fewer living systems you carry, the more of the design can be optimized around propulsion rather than survival. The catalyzed branch helps for a similar reason. When antimatter is treated as a trigger rather than the bulk fuel, the spacecraft stops asking one impossible system to do every job at once. A nanogram scale supply is still hard, but it is a very different industrial ask from a gram scale supply. A trap that protects a trigger inventory is still an active machine, but it does not dominate the ship the same way a mission fuel trap does. The engine still has to handle violent energy release, but it can lean on the rest of the fission or fusion hardware for most of the thrust and most of the propellant mass. The result is less elegant on a poster and much more believable as an engineering road. That helps explain why antimatter persists in serious papers without becoming a real program line. The concept is useful as a hard boundary case. It tells researchers what happens when energy density stops being the limiting term and all the secondary terms take over. It makes the hidden penalties impossible to hide. If you want to understand how much of a Mars mission is really about propellant and how much is about shielding, heat rejection, reliability, and braking, antimatter is a brutal teacher. It strips away the excuse that the fuel was too weak. Then it shows that the spacecraft is still hard. The calmer conclusion is the useful one. Antimatter is not a near-term crude Mars engine. It is a long-horizon propulsion family with one realistic near-term branch, which is antimatter catalyzed systems, and one much harder branch, which is pure annihilation drive concepts. If production, confinement, and heat handling improve by orders of magnitude, the balance can change. For now, the honest design answer is that antimatter teaches us more about the cost of fast spaceflight than it offers a ready vehicle. Return one last time to the ship in low orbit. The trip clock is still counting in months. The crew is still inside their small habitat. The route to Mars is unchanged. What changed was the vehicle wrapped around that trip. The engine became a radiation source. The fuel became a confinement problem. The fast route became a longer list of systems that all have to work at once. So what does antimatter really buy? First, it buys a real upper limit on fuel energy density. The headline number is not fake. Matter-antimatter annihilation releases more energy per kilogram than chemical fuel, fission fuel, or fusion fuel normally discussed in mission studies. That part is solid physics. But the rest of the answer lives in the penalties attached to turning that energy into a working spacecraft. Those penalties are the whole story. You have to manufacture the fuel at a scale no one has demonstrated. You have to trap it without losing it. You have to survive the radiation coming out of the engine. You have to dump the waste heat. You have to carry enough propulsion to slow down when you arrive. If people are on board, every one of those requirements gets harder. By the time the vehicle is honest, the fuel advantage is still there, but it no longer looks like a shortcut. That is why the most credible near-term use is the small one. A tiny amount of antimatter can serve as an igniter inside hybrid concepts where conventional nuclear fuel still does most of the heavy lifting. That is a narrower claim than the slogan, but it is a much stronger one. It fits the production problem better. It fits the storage problem better. It fits the way real propulsion programs usually advance, which is by accepting a partial win before attempting the extreme version. Pure antimatter propulsion remains worth studying for a different reason. It is a clean way to expose the rest of the spacecraft problem. If even the most energy-dense fuel imaginable still runs into shielding limits, radiator mass, trap reliability, and braking burden, then those are the real hard parts of fast deep space travel. Antimatter does not remove them. It makes them impossible to ignore. There is a useful discipline in ending there instead of with a slogan. A lot of advanced propulsion talk assumes that if the fuel gets good enough, the rest of the mission will sort itself out. This topic is a good correction. The rest of the mission does not sort itself out. The engine layout gets harder. The ship gets longer. The system's budget gets tighter. The failure tree gets uglier. The arrival burn still has to happen. A dense fuel can remove one bottleneck and still leave every other bottleneck standing. That is why the crude Mars framing matters so much here. Mars is close enough that engineers can compare antimatter against plausible alternatives instead of against fantasy. Nuclear thermal propulsion might shorten transit without demanding antimatter storage. Electric cargo stages can move bulk mass slowly while crew rides a different vehicle. Chemical systems remain clumsy but well understood. In that comparison set, antimatter has to do more than sound powerful. It has to close a mission better than the other options, once mass, heat, shielding, schedule, and reliability are all counted together. Today it does not. For robotic deep space work, the answer opens a little. A probe aimed at the outer planets, the Kuiper Belt, or some future high delta-V rendezvous can accept a stranger vehicle if the science return is high enough. A robotic architecture can also tolerate higher risk and lower redundancy than a crude one. That does not solve the production problem, but it does make the mission logic less hostile. If antimatter ever becomes operational, that is one of the first places it is likely to appear. Not carrying people to Mars, but pushing instruments where slower systems are too limiting. There is also a reason to keep the question open even if the present answer is conservative. The supporting technologies are not frozen. Better superconductors could reduce magnet mass. Better cryocoolers could reduce the support burden of long-duration traps. Better beam handling could improve how antiprotons are captured and slowed. None of those changes would solve the whole problem, and none of them is close to solving it today. But they are the kinds of advances that would have to arrive before antimatter moves from a concept study subject to a vehicle program. Watching those pieces is more useful than repeating the slogan. And even then, the order of progress will matter. A breakthrough in production without a breakthrough in storage still leaves the mission stranded in orbit with unusable fuel. A breakthrough in storage without a breakthrough in heat rejection still leaves the vehicle too heavy and too fragile. A breakthrough in both without a practical braking architecture still leaves the ship able to leave and unable to arrive. Antimatter is one of those topics where partial success does not immediately turn into a mission. Several different hard problems have to improve together before the answer changes. So the simplest answer is this. Antimatter could help take us deeper into space, but not in the sleek near-term form that popular summaries suggest. In the nearer future, its best role is probably as a trigger inside hybrid nuclear systems. In the farther future, pure antimatter propulsion remains a serious but remote engineering possibility. And right now, its biggest value is that it shows exactly what a fast deep space ship would still have to pay for.